First, let's get a look at the data we're working with in this demo. You can see a headline figure of nearly 800 billion records. This represents 2 days of weather forecast data. It's a global model, which means for this data set we have data points covering the entire globe. You can see the data set contains different types of measurements, wind direction, soil temperature, air pressure, and provides this for different heights, pressure and depth. It means we have for every hour forecast over 3 billion data points that can be addressed. You can see here that this data is stored for this example in a single table with forecast time and time being forecast linked to a measurement value for a given latitude and longitude. As you can see, these interactive notebooks are a great way of visualizing some of the complex queries. We start off with the Python code defined but not executed. We're using a number of open source libraries which will be recognizable to anyone who is working with geospatial data. These are able to interact with the data stored within Ocient using our JDBC driver contained within the PyOcient package. As we go through the example queries, you will see that all the SQL being executed is contained within this notebook, with the data and queries themselves sitting what we would consider to be in an entry-level Ocient platform containing 4 foundation nodes. The foundation nodes are the heart of Ocient Compute Adjacent Storage Architecture, providing CPUs with direct access to NVMe drives capable of over 1 million IOPS and gigabytes per second of throughput, critical for the hyperscale workloads we are built to deal with. What we're going to show in this demo is Ocient's ability to make these vast geospatial data sources accessible. Whilst that may not sound complex at first, the requirements in the space see the generation of trillions of data points every day. Datasets quickly start to run from terabytes into petabytes, and it is very difficult to give access to significant portions of this data in any meaningful way. These examples demonstrate our core capabilities in this space and show how you can continue to use tools you are comfortable with to unleash the power of Ocient and run complex, meaningful mathematical analysis on massive datasets, all without moving the data. Okay, so I'm just going to kick off the notebook, and I'm going to just hit run all now, and that will execute all of the queries that we've got defined here, one after the other. You can see at first, obviously it's pretty standard. We're loading the credentials, we're starting to define a connection string to the database, and then we're getting into actually running the queries on this data as well. So one of the first things we wanted to demonstrate is very simple geospatial filtering. So obviously we're talking about a massive data set here, but this query itself, it's going to do an aggregate measurement, in this case on air pressure, and it's going to do that by a specific area. And you can see here that we are defining that area as a polygon on those latitudes and longitudes here. So for this polygon, we're taking our data set of 800 billion records. We are using our filtering to very quickly, within 4.6 seconds, reduce that forecast count down to the 3 billion records we discussed, and then down to the specific measurement, and within that time we then can do the computation, and we're giving an average air pressure in this case of 102,000 pascals. Okay, so the next example we're going to look at is interpolation. Different projections obviously will have different mapping points when it comes to globes, 3-dimensional, 2-dimensional, etc. So we're taking a theoretical point in this example that doesn't exist in the data set that we have today, and we're going to do a 3-dimensional interpolation on that data within the database in order to generate a new data point. So we've broken out all of the SQL here just to demonstrate the complexity of this. Obviously this can be simplified, within actual any production running of the data, but as you can see, in order to do this, we're taking data from all of the different data points we have. We are identifying points around the theoretical data point, and then we're weighting all of those different data points in order to produce a final value. So again, we're talking about the 800 billion record database, and we're able to filter that down, take all of the correct data points within that data set, and produce an averaged interpolated metric within that time as well. So from here the examples start to become a little bit more practical, and the intention of these examples is to kind of build on a theme of what we can do in the database. So The idea being that within all of the data that is stored, we're going to be looking for points of interest, areas of weather that are interesting, which from a human being and visual representations, whether that's satellite data that you're looking at or other weather forecast data that's being represented, it's quite easy to see where the areas of interest are, because you can see the cloud formations, or you can see high areas of variance because they've been mapped. But doing that mathematically and doing it in a way that would allow you to do this at scale is a different level of problem. And so what we're looking at here is wind momentum, and the first thing we're trying to do is just simply map the wind momentum at all points on the globe. So we're using open source tools here to do that, and you can see that once we run the query, we pull out all the data points for wind momentum for a given forecast. We're then able to map that on a globe, and you can see here that the momentum's anything from 0 to 56, and the really light areas are the areas of interest. And as I said before, so from our perspective now, you can see that there's some interesting areas, but understanding that mathematically is slightly different, and obviously that's what we'll now go on to demonstrate. So I should note that we were able to execute that pull of all the data points in less than a second, obviously filtering it down to a single forecast data point. You'll see that clearly the command in this case took 45 seconds. Some of that delay is that we've got quite a number of data points to load into the actual laptop I'm running on. So some of the delay is in that happening as well. So we know we can take all of the data points and map the areas of extreme wind momentum, but now we have to actually identify which areas are the extreme points. And so you can see here in this query, what we're starting to do is we're starting to compare all of the data points, and we're giving them effectively a score of how many different deviations above the norm are some of these points. So that allows us to pick out the areas of extreme values, effectively the areas of extreme wind momentum. And again, we can plot that on a graph. So here you can see, and correlating very similarly to some of these areas that we've seen on the previous view, we are starting to identify those extreme points of wind momentum. So we do have dots upon the globe, which we can now actually visualize. But again, from plotting an area of interest, we do need to go further. So what we're going to do now is group these areas into clusters, and the reason to do that is to basically mathematically identify and geospatially identify which of these interesting data points are together. I mean, again, going back to my point, you can see very easily that they are, and these are, and those are. However, from a mathematical perspective, you then need to consider their location within the globe and how close they are to each other in order to actually do that. So that's something we do by using one of the geospatial functions we have in the database. We're simply looking for data points that are clustered together, and are clustered together within 100 kilometers of each other. And if they are, and there's enough of them, then we're in a situation where we're going to class that as a cluster. So again, 5 seconds later, we're able to take this data set, we're able to filter it down, and we're able to identify that. And so this is what is represented here on this map. You can see the different numbers. We've given an ID to each of the clusters, different color, and there they are highlighted as clusters. So all of those data points are grouped together based on this, and that's important moving forwards. So we now have those clusters, we now have all the data points mapped and grouped together. What we're able to do now with the data is effectively throw a polygon around that group, and that ultimately defines the area of interest. So again, we're running the same command and we're building on top of this. We've identified the points of interest. We are identifying the clusters of those points of interest, and then we're finally using another one of our internal geospatial operators, convex hull, in order to effectively put a polygon around the area which that data covers. And when we do that, this is what you can see. So we've moved from data points now to actual polygons which represent those areas, and you now have geospatial locations in which you can now look and you can apply to other data sets or to other features. So you can imagine it being very easy now to do a filter on all those different polygons and taking data from other data types, whether it be air pressure, wind speed, and seeing if there's any correlations. That is very simple from this point on.